Hey, glad you could join us. It's always nice to have some company while we float through the stars. There's something comforting about sharing a quiet moment like this, even across vast distances. Thanks for making the time to be here. I know life gets busy, and choosing stillness is a gift. So settle in, get cozy. This is your moment to breathe deeply and just drift for a while. Wherever you are under a blanket, sipping tea, or watching the sky, I'm glad you're here. If you like listening to quiet stories about space and stars, please tap the like button. It helps others find this peaceful place too. And if you want to come back for more calm journeys through the universe, please like and subscribe. Enjoy what I do here, and let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Hey everyone, today we're looking into stars, and something far stranger that hides behind them. You and I are going to wander into a place where gravity stretches the very shape of time. A place so strange, so quiet, so unknowable, that even light can't find its way back. Black holes. And not just any black holes. We're going to drift slowly into the question, do black holes really destroy time? You don't need to pack anything, just your imagination, and maybe a little curiosity. We're explorers in this journey, discovering not only black holes but the very essence of what it means to move through time. The more we learn, the more we realize time isn't a simple, fixed line but a living, twisting thread woven into the universe's grand design. Imagine that you're still falling inward, deeper into that shadowy realm where space and time blend. The light around you dims, not because it's getting darker, but because everything is stretched and distorted, like a painting slowly melting. Time itself begins to play tricks on your senses. Seconds might feel like minutes, minutes might stretch into hours, or perhaps everything compresses into a single, endless moment. Scientists have long wondered how exactly time behaves in these extreme conditions. Some suggest that near the event horizon, time slows down so much that, from the perspective of an outside observer, you appear frozen, stuck in a moment that never quite passes. Yet for you, inside, time feels perfectly normal, flowing like a steady river, even as it pulls you inevitably forward. Feel that paradox settling around you. The outside world sees you as a still image, while inside, your thoughts and sensations continue, full and alive. It's a reminder that time is not just something out there, ticking on clocks. It's something deeply tied to where you are, how fast you're moving, and the gravity you're under. Gravity, you see, is the key player here. The intense gravity of a black hole warps time and space alike. This warping isn't just a theory on paper. It's been observed through light signals from stars dancing near black holes, showing their clocks run differently than ours. Picture a star in a tight orbit around a black hole. As it swings closest, its time slows compared to a distant observer's clock. That star is living in a kind of cosmic time bubble, experiencing a different pace of life shaped by gravity's grip. But what about the very center of the black hole, the singularity? This is where all known physics gets fuzzy. Our best theories predict an infinite density and gravity, crushing everything into a point of zero size. But infinity is a tricky idea's own thing our current understanding can't truly grasp. Here, some scientists hope that a theory of quantum gravity, something combining Einstein's gravity with quantum mechanics, will reveal what really happens to time and space. Will time stop? Will it loop? Or will something even stranger unfold? Something we can barely imagine. Imagine being inside this unknown, where the usual flow of seconds and minutes might dissolve entirely. Time might not have a beginning or an end, or it could spiral endlessly. It could be like stepping into a hall of mirrors, where reflections of past and future blend and multiply. And yet, black holes don't just swallow time, they might also preserve it in surprising ways. Consider Hawking radiation, a subtle glow emitted by black holes over immense timescales, discovered by the brilliant physicist Stephen Hawking. This radiation suggests black holes slowly lose mass and energy, meaning they can evaporate over billions or even trillions of years. If black holes disappear in this way, what happens to the information swallowed inside the details about everything that fell in? This question is at the heart of the famous information paradox, a puzzle that has kept physicists debating for decades. Does the information vanish forever, destroying time's records? Or is it somehow encoded in the Hawking radiation, subtly preserved as the black hole fades away? This puzzle ties back to time itself if information is lost. Does time break its own rules? Does the past get erased? Imagine the universe as a giant book. Each event, every particle, every second, is a line written on its pages. If black holes erase some of these lines, does the story lose coherence? Or does the book have hidden margins where these missing lines are secretly kept? These are the questions that keep us fascinated, drawing us closer to the heart of black holes and the nature of time. Feel the pull of curiosity as we stand at the crossroads of physics and philosophy, where time isn't just a measure, but a mystery wrapped in gravity's embrace. As we continue this cosmic journey together, remember that every new insight brings more wonder. Black holes challenge our understanding and invite us to rethink what time means, how it flows, and what it truly is. Picture yourself now, past the point of no return, drifting deeper into the heart of the black hole. What happens next is a topic of much speculation, a mystery wrapped in scientific theory, imagination, and a sprinkle of wonder. One idea suggests that as you near the singularity, the fabric of space and time becomes so warped and twisted that what you think of as after might not even make sense anymore. It's as if you've stepped into a place where the rules that govern your world cause and effect, past and future, begin to blur and merge. Some scientists propose that the singularity might not be a single point but a bridge, a kind of cosmic tunnel connecting our universe to another place, or even another universe. Imagine that after falling into a black hole, you might come out somewhere completely different, maybe a new universe with different laws of physics, a place of fresh beginnings and strange new possibilities. This idea is linked to the concept of a wormhole. Think of a wormhole as a shortcut through the fabric of space, a tunnel with two ends, each in separate points in space and time. If black holes are one end of such tunnels, could the other end be somewhere else entirely? It's a thrilling thought. You could be traveling through the depths of a black hole and emerge somewhere unimaginable, perhaps in a far-off galaxy, or even a new dimension. It's a cosmic gateway, a doorway not just through space but through time itself. Another fascinating theory comes from the world of quantum mechanics. Some physicists believe that the intense conditions inside a black hole cause space-time to behave like a quantum foamer, frothy, ever-changing surface where particles and waves pop in and out of existence. In this foam, the singularity might be smoothed out, rather than being an infinitely small point. Time itself could become fuzzy, and instead of ending, it might loop or twist back on itself. Imagine time bending into a circle, or spiraling in a way that makes every moment both before and after simultaneously. From this perspective, the after inside a black hole might be a place where time loses its linear flow and becomes a landscape you can explore in many directions. A cosmic Mobius strip where past and future fold into one another. Then there's the intriguing idea of black hole complementarity, which tries to reconcile how time seems frozen for an outside observer while continuing normally for someone falling in. According to this, both perspectives are correct but apply to different realities. The black hole might be a kind of hologram, where all the information about the inside is somehow encoded on its surface. In this sense, what happens after could be a reflection or projection. Your journey inside the black hole might exist both in the depths and on the boundary at once, challenging our understanding of time and existence. Imagine standing in a place where every step you take forward is both inside and outside, here and somewhere else, now and a moment later. It's a puzzle that teases the mind and invites endless exploration. And what about the fate of matter and energy swallowed by the black hole? Some theories propose that they might be transformed or recycled in ways we don't yet understand. The black hole could be a cosmic engine, converting what falls into new forms of energy, or even seeding the birth of new stars and galaxies somewhere else. This possibility paints black holes not as destroyers, but as creators, guardians of cosmic cycles where time and matter flow endlessly, changing shape but never truly ending. Imagine the deep hum of the universe's heartbeat, pulsing through black holes as they turn endings into beginnings, transforming time itself into a never-ending story. So, as we drift through these vast ideas, you can feel the awe and mystery that black holes inspire. They challenge us to rethink time, not just as a steady clock, but as a fluid, mysterious journey with twists, turns, and endless possibilities. There's so much more to uncover beyond this point, And with every new theory, we peel back another layer of the universe's grand design. Imagine yourself carried relentlessly inward, crossing the event horizon and moving ever closer to the singularity, the heart of the black hole. This place is unlike anything else in the universe, a place where our usual ideas about time, space, and reality break down. But what exactly could be waiting there, and how long would it take to get there? First, think about the sheer scale of the journey. While the event horizon marks the point of no return, the singularity itself lies at the center, often imagined as an infinitely dense point. Depending on the size of the black hole, the distance from the event horizon to the singularity can vary greatly. For a small black hole, say one with a mass a few times that of our Sun, this inward journey from horizon to singularity might be surprisingly quick, only a fraction of a second from your perspective. It's as if you're on a cosmic elevator that descends rapidly into darkness, with time stretching and twisting as you fall. But for a supermassive black hole, like the ones at the centers of galaxies weighing millions or even billions of times the Sun's mass, the story changes dramatically. The event horizon can be so vast that falling inward might take hours, days, or even longer, at least by your own experience. Feel yourself floating, falling deeper, sensing that the larger the black hole, the gentler its pull feels near the edge. Time might feel almost normal for a while, giving you more moments to look around as the stars behind you fade into a shimmering halo. Yet, no matter the size, the singularity remains an ultimate destination, a place where gravity crushes everything into an unimaginable point, and our current physics fails to describe what happens next. What could lie at this end is one of the biggest mysteries in science. Some theories say it's a point of infinite density and zero volume where space and time as we know them vanish. But infinities are tricky ideas. They signal the limits of our understanding, not a final answer. Other ideas suggest the singularity might not be a point at all. Instead, it could be something more complexer, quantum fuzz, where the laws of quantum mechanics smooth out the infinities and create a new kind of space-time fabric. In this fuzzy core, time might loop, rewind, or merge with space in ways that defy imagination. Picture this place as a cosmic seeder, potential birthplace of new universes or dimensions. Some speculative theories imagine black holes as cosmic wombs, where the collapse inside creates baby universes, budding off from our own, each with their own flow of time and space. If this is true, the end of a black hole isn't an end at all, but a gateway, a bridge to something entirely new. Time inside might reset, begin again, or exist outside our normal understanding. But what about the experience of time itself? How does time pass as you fall inward? From your own viewpoint, time might slow or even stretch out, especially near the event horizon. This effect, called gravitational time dilation, means that while seconds might feel normal to you, an outside observer would see your fall stretching into a never-ending slow motion. Imagine being frozen in time from afar, while you plunge deeper and deeper, racing toward the singularity where time might speed up or break down entirely. And here's a fascinating twist. Because of these time effects, black holes might last incredibly long from our perspective. Some could endure for billions or trillions of years before evaporating through the slow process of Hawking radiation. Picture the slow, faint glow of Hawking radiation as a cosmic whisper, a signal that even the mightiest black holes are not eternal but slowly fade away, taking with them the secrets of time trapped inside. So, the end of a black hole is not just a distant point in space, but a profound question about the nature of time itself. Will time end there? Will it loop? Or will it spark the birth of something new and mysterious? Imagine standing on the edge of this mystery, feeling both the pull of gravity and the pull of curiosity, knowing that the journey through time and space inside a black hole challenges everything we think we know. Let's begin somewhere gentle. Above us, stretched like an old soft quilt, the night sky is glowing with the light of stars so far away. Their messages have taken millions of years to reach us. 1 star, 2 stars, thousands. Now picture them not as distant pinpricks, but as blazing, thunderous furnaces, each one boiling with ancient fire. Some of these stars are already gone, long gone, but their light is still arriving. That's the first little clue we'll tuck into our pocket tonight. Light takes time. Time and light travel together, like old friends on a road trip. So what happens when they run into something that doesn't like visitors? Let's head there now. Not too fast. Feel the silence grow thicker as we pass beyond the stars, into deeper space. Here, the stars grow sparse. Space darkens. Then something shifts. You might not see it, not at first, but reach out. Do you feel that? A slow pulling, like the space around us is subtly leaning in one direction. That's gravity, but not the soft kind that holds your feet to the earth. This is gravity wound up tight, concentrated, dangerous. We've just felt the edge of a black hole's presence. It's not chasing us. It doesn't need to. It's simply there, and everything nearby knows it. Let your gaze wander. There's no color here. Not really. Just a slow swirl of crushed starlight bending inward. Even sound feels thinner, but not because there's nothing to hear. It's because time itself is behaving differently. Stand still here with me, just at the edge of the event horizon. That's the point of no return. The invisible surface of a black hole. Anything that crosses it doesn't come back. Not people, not planets, not even light. But something even stranger happens here. Time, that thing we feel ticking in our chest. In the sun's path across the sky, in the laughter of a growing child, it begins to slow. Let's sit here for a moment. Feel how thick the silence becomes. If we had a clock, it would tick. More. Slowly. Tick. Tock. And then maybe stop. But only from our view out here. Someone falling in would feel normal. Their watch would work just fine. They'd blink, breathe, speak all at regular speed. But to us, watching from the outside, they'd seem to freeze, forever hovering just above the edge. That's the first taste of time being stretched. Not broken, not shattered, just tugged like taffy in a cold, invisible wind. Let's float closer, carefully. There's no rush. As we drift toward this strange place, listen to the soft hum of distant galaxies curling like smoke on the cosmic wind. The universe is still moving all around us, full of color and light and birth and destruction. But right here, time feels like it's shivering. Here's something wild. Black holes don't destroy time like stepping on a clock. They bend it, curl it, loop it. If you dropped a ball into a black hole, it might never reach the center from our point of view. From its point of view, it might fall straight in, gone in an instant. So whose time is real? Yours? Mine? The ball's? That's the question we'll unravel slowly, like peeling apart a dream, not with big words or formulas, just with quiet curiosity. All right, that's the first one, 200 words of our 100-word journey. If this feels right so far, I'll continue generating the rest in this exact tone and rhythm until we reach the full length. So, here we are resuspended near a black hole, in this silent place where time isn't quite what it used to be. You might feel a kind of stillness in your bones, like the whole universe has taken a slow breath and decided not to let it go just yet. The light bends around us in a lazy spiral, and even though we know it's moving at incredible speed, it feels like it's crawling. That's not just your imagination, it's what time does here. It slows, twists, stretches. Now, if you could pull out a stopwatch and somehow compare it to one left far away from this black hole, maybe on Earth, you'd see something curious. The stopwatch near the black hole would be ticking slower, just a little at first. But the closer you got, the more dramatic the difference would become. A second here might be a minute there, then an hour, a day, a century. And yet, from your point of view, it would all feel completely normal. Your thoughts wouldn't slow down. Your breath would rise and fall the same way it always does. That's one of the strangest things about black holes. They don't make your time stop. They change how your time looks to someone else. Now imagine this. If you hovered just barely above the event horizon, time for you would pass as usual. But from someone watching you from far away, you'd appear to be moving slower and slower until if you stopped right at the edge, you'd freeze. You'd stay there forever, right on the edge of falling in. From their view, you'd never quite vanish. But from your view, well, you'd keep going. That edge is called the event horizon. Not a wall, not a surface, just a boundary. A place where time and space flip their usual roles. On one side, everything still behaves in a way that makes some kind of sense. On the other side, nothing ever comes back. Not because it's trapped in a cage, but because space is folding inward so strongly that even light can't find the road out. You and I, we're just hanging out above this edge, safe, watching, wondering. Let's reach out, not too far, and feel the space around us. It's not cold in the usual way. It's something deeper, a kind of absence, like walking into a room that forgot it ever had furniture. It's not hostile, but it's not exactly friendly either. It just is. And here's something beautiful. Black holes aren't just dangerous. They're also a kind of memory, a cosmic reminder of a star that once lived, breathed, burned, and died. Most black holes come from stars that were much larger than our sun, maybe 10 times the size, or more. When they run out of fuel, they collapse. Gravity wins. And when that collapse goes far enough, it creates something so dense that even the idea of escape becomes meaningless. We call it singularity, the heart of the black hole. But nobody really knows what happens there. Some say time ends, others say time begins. But let's stay where we are for now, right near the edge, and keep watching. See that speck of light falling in? It used to be a piece of a star, maybe the last bit of a supernova. It's been drifting for thousands of years, pulled along by gravity like a leaf down a river. And now, it's falling into the black hole. From here, it seems to slow down, doesn't it? It stretches, smears out, glows a little brighter. That's because of something called gravitational redshift. Though we won't get technical, just know that the black hole is stealing the light's energy, bending it, stretching its color until it fades into invisibility. And the moment it touches the horizon, it's gone. Not torn, not burned, just no longer visible. Still there, somewhere deeper. But outside of space, and outside of time, as we know them. You might wonder, does anything escape? Is it really a one-way trip? Well, here's something delightful to ponder. A long time ago, people believed black holes were completely sealed, but then came a little whisper from a scientist named Stephen Hawking. He showed that black holes might leak, just a little, just a whisper of heat. We call it Hawking radiation, and while we're not diving into formulas, the idea is this: black holes might not live forever. They might shrink, evaporate, fade. But that takes an astonishingly long time. For a black hole the size of a mountain, it would take longer than the current age of the universe to disappear. For one the size of a star, longer still. But the idea is there. Maybe nothing is truly forever. Not even these great swallowing voids. Still, the big question hangs in the air between us. Do black holes destroy time? Let's keep feeling it. Let's glide a little closer. You see, black holes don't just mess with time, they mess with order. If you dropped a photograph into a black holy picture of someone you love, would that memory be erased? Or is it still there, hidden behind the curtain? Some physicists argue that information can't be destroyed, that somewhere, somehow, every bit of data that falls in must still exist, maybe smeared along the horizon like a shadow, maybe folded into the tiniest fabric of the universe, but others think it's gone, lost, not in the usual sense, but in a fundamental one. If that's true, then yes, black holes might destroy something more than time. They might undo stories, rewrite history, silence memories. But no one knows for sure. You and I, we're lucky. We get to wonder, to sit here in this calm void and dream out loud. No rush, no pressure, just curiosity, floating like dust in a sunbeam. Let's look around again. Off in the distance, galaxies spin like pinwheels on an invisible wind. Each one contains billions of stars, and around many of those stars are planets. And on some of those planets, maybe just maybe someone else is also wondering about time. Maybe they're telling stories like this one. Maybe they're watching their own black hole and asking the same question: what happens when time runs out? Feel how the silence here isn't empty. It's thick with possibilities, with questions. Now, imagine if we could survive falling in. Just imagine it. We float gently through the event, horizon not torn, not crushed, just moving inward. What would we feel? Some say we'd drift toward the center, toward the singularity, where time and space get so tangled they stop making sense. Others say we might pass into another place, another universe, another reality altogether. Some theories suggest black holes could be gateways, not just dead ends, but bridges, wormholes, tunnels between stars, or between times. It's not science fiction. It's an idea that lives on the edge of what we know, But no one's ever tested it, of course. It's hard to send a postcard from the other side of a black hole. Still, the idea is comforting, isn't it? That maybe even the scariest things in the universe might lead somewhere new. And so, does a black hole destroy time? Let's pause. In a way, yes. At the center, where the singularity lies, time as we understand it may not exist. There may be no before or after, no ticking clock, just something else. Something we don't have words for yet. But outside the horizon, time still flows, twisted, bent, stretched but still flowing, like a river near a waterfall, speeding up, slowing down, pulling itself into impossible shapes. But it moves, and that's the mystery we're floating in. Let's stay here a little longer. Feel the gravity, not as pressure, but as a hush, a presence, something that asks nothing, promises nothing, but holds everything. Listen to the silence between the stars. It has weight, and that weight somehow knows your name. Take another slow breath here with me. We're weightless, adrift just above the event horizon, where time behaves like a soft ribbon caught in a whirlpool. Watch it spiral, not in panic, not in violence, just slowly, gently, like it's being called inward by something it cannot resist. And now, let's tilt our heads back and look away from the black hole for a moment. That's right. Turn slowly. See the stars again, spread out behind us in their thousands and thousands. They twinkle not because they flicker, but because their light dances through waves of invisible space dust. And that light, the same kind we use to see everything in the universe, it's being stretched to by the black hole behind us. The farther away you look from this deep gravitational field, the more that light returns to its usual rhythm. It regains its energy. Time outside the black hole is still flowing as it always has. Somewhere far from here, a kettle is boiling, a child is blinking, a cat is leaping from a windowsill. But here, close to this dark tide, all of that feels impossibly distant. You and I, we're in a strange pocket of the cosmos, one that doesn't shout or sparkle, one that swallows. But that doesn't mean nothing is happening here. Quite the opposite. Let's glide slowly in a circle now, orbiting this black hole at a safe distance. We're not falling yet, just drifting around the edge. You might notice something interesting. We're not alone. There's a disk here, glowing faintly, a thin, radiant ring spiraling around the black hole like water circling a drain. That's called an accretion disk, not a name we need to worry about, but you can think of it as the black hole's dinner plate. It's made of gas and dust and broken bits of stars, all spinning incredibly fast and heating up until they shine. And the glow is intense, brighter than you'd expect from something so dark. In fact, the area around a black hole can be one of the brightest spots in the universe. Imagine that. A light show built around darkness, a silence wrapped in sound. It's not the black hole itself that shines, it's what's dancing around it. Lean a little closer and listen, not with your ears but with your imagination. Hear the storm of movement, the crashing of matter in motion, the swirl of glowing chaos just before the plunge, all of it rushing and roaring around the invisible middle. It's beautiful, in a haunting kind of way. And now, let's bring time back into our thoughts. Because right here, in this ring of fiery debris, time moves differently too, just like it does for us. Everything caught in this orbit feels the grip of warped time. The closer it gets to the event horizon, the slower time becomes from an outside view. That means if you were standing far away and watching a star fall into this black hole, you'd never actually see it fall in. You'd see it slow and slow until it seemed to stop, right on the edge, trapped not by force, but by time itself being stretched until it freezes. But to that star, its journey would continue. It would pass through the event horizon without any Dramano flash, no explosion, just motion, just falling, and then something unknown. That's the dual nature of time here. For the falling thing, time continues. For the watcher, time stops. And that might be the most poetic truth in the universe. That time doesn't vanish inside a black holite, just stops making sense in the way we expect it to. Let's sit still here for a while and talk about how black holes shape more than just space and time. They shape the story of the universe itself. Black holes are not rare. There's likely one in the center of almost every galaxy, including our own Milky Way. That's right now. As you and I are floating here, our home galaxy is spinning quietly around a supermassive black hole called Sagittarius A. Don't worry, it's not coming for us. We're too far away, but it's there, calm, still, and holding everything together with its massive pull. That black hole has the mass of 4 million suns. 4 million. But it takes up less space than a star would. It's tiny compared to its weight, so dense, so heavy, that space folds in around it. And time, as you might guess, is dragged along like a scarf in the wind. Now imagine this. If you could orbit safely around that black hole for a while, just like we're doing here, and then return home, centuries could pass for the people back on Earth. But for you? Maybe just a few hours, maybe a day. That's not just a story. That's a real prediction of how gravity stretches time. It's called time dilation. Not a big word we need to memorize, just a gentle reminder that the stronger the gravity, the slower time flows nearby. So no, time isn't destroyed. Not really. But it is sculpted, molded, bent. Let's wander inward again. Float softly. The black hole is ahead of us, silent and still. You might feel a little chill, but that's just your imagination sensing the absence of light. There's no color here, no sound, just a perfect quiet. Reach out, just for a moment. Not too far. Let your fingers feel the edge of gravity's breath. Time is thin here, almost syrupy. And here's a strange thought. If you could fall into a black hole and somehow survive, some physicists believe all paths would lead you to the center. No matter where you aim, you end up there. That's because, inside the event horizon, space and time swap roles. Time becomes something you move toward, like a direction, like north. You can't avoid the singularity because it's not just a place, it's a moment in time. And like all moments, once you're moving toward it, there's no turning back. That's why some people say black holes don't destroy time, they are time. Or at least, they represent a place where time becomes pure direction. But others argue something more dramatic. They say that at the singularity, the laws of the universe break down, that time does end, that no clocks can tick there, that no cause leads to effect. It's a place where meaning and motion dissolve. And if that's true, then yes, maybe black holes do destroy time, but only at the very, very center. Everywhere else, time flows, bent, curved, strange, but flowing. Look around again. You might spot a jet of light shooting out from the black hole's poles. That's real. Some black holes, especially the supermassive ones, shoot out enormous beams of energy into space jets that stretch for thousands of light years. And yet, they come from something that doesn't let light escape. How is that possible? Well, those jets don't come from inside the black hole. They're made from the superheated material spinning in the accretion disk just outside it. Magnetic fields twist and snap, launching energy into the cosmos. These jets can be so powerful that they light up entire galaxies. It's a lovely paradox, isn't it? Something made entirely of darkness, surrounded by some of the brightest objects we know. So maybe black holes don't destroy light, they frame it. Maybe they don't end time, they outline its limits. And maybe, just maybe, they don't erase stories, they help write them. We're getting closer now, still hovering safely, but if we wanted, we could fall in. No pain, no drama, just motion. And once we crossed that edge, there would be no coming back. No messages, no signals, not even a flicker. We would be part of the black hole, part of its memory, part of its silence. And yet, the universe would go on. Because while time bends and stretches near a black hole, it still moves forward elsewhere. Out there, stars are being born in clouds of gas. Planets are forming, comets are drifting, galaxies are colliding. Time is everywhere. And even here, wrapped around this dark mystery, time still leaves a trail. You can feel it, can't you? Like the soft ticking of a clock you can't see. Let's rest here for a while. Let's float. You've done wonderfully so far. We're not done yet, not even close. There's so much more to see. So stay with me. Let's keep drifting deeper together. Let's stay here in this strange, quiet orbit for just a while longer. Time may be moving oddly around us, but that's okay. We're in no rush. In fact, the farther we float from the usual pace of things, the easier it becomes to just observe, to really notice. Out in the distance, a star flickers, not because it's uncertain, but because something, maybe a field of gas, or a planet-sized shadow, is passing briefly in front of it. In deep space, light is always dancing, always filtering through things we can't quite see. And that's the thing about space. There's more of the unseen than the seen. For every star we notice, there are countless more hidden behind dust, gas, or simply distance. And near black holes, even more is hidden. Let's lean in closer to the swirling disk of matter that hugs this black hole like a slow whirlpool. It's not flat and calm. It's messy, heated, wild. You might imagine flames, but this isn't fire. It's friction, gas particles slamming into each other, heating up to millions of degrees, spinning at nearly the speed of light. That's fast enough to turn matter into light, not in theory and reality. That's why these disks shine so brightly, why we can detect them from galaxies away. They're some of the brightest continuous sources of energy in the entire universe. Not the black hole itself, but what it's feasting on. And here's a fact to wrap your mind around gently. That spinning ring of light can tell us about the black hole's mass, its size, and even how fast it's rotating. Yes, black holes can spin. Some of them spin so fast that the fabric of space itself is being dragged around with them. This effect is called frame dragging, though we won't get lost in the name. What matters is the image. Imagine a black hole not just as a sphere, but as a whirling storm, so powerful that even space-empty, invisible space is pulled around it like syrup circling a drain. And where space is dragged, time goes too. That's why a spinning black hole warps time even more dramatically. If you were to orbit one in the same direction it spins, you'd experience time slower than someone orbiting against the spin. Think about that. Just changing your direction could change how time moves for you. Not just seconds, years. In theory, some rotating black holes might even have a region outside the event horizon called the ergosphere place, where nothing can stay still. Everything must rotate. Not because it's moving, but because the black hole is pulling the very fabric of space around with it. Let's drift toward that space now. Feel it? Not movement in the usual sense, but a kind of invisible tide. You don't need to swim or steer, you're simply part of the current. And you might be wondering now, could we use that? Could we somehow turn a black hole's spin into a way to travel through time? That question has sparked 1,000 quiet debates among the people who think about such things for a living. Some believe it might be possible to slingshot around a spinning black hole in just the right way, so that you loop forward in time. Others think the forces involved would tear anything apart long before it could make the trip. Still, it's a fascinating thought that time travel might not require a machine, just gravity and patience, and a willingness to pass near the edge of something no one fully understands. Let's not fall in just yet. Instead, let's glide above this storm and look outward. The stars behind us look curved, don't they? Warped around the black hole like their reflections are trapped in a funhouse mirror. This is real. Black holes bend light itself. This warping is called gravitational lensing. It's not a trick of the eye, it's gravity acting on the path of light, bending it the same way a glass lens bends sunlight. And sometimes, if the alignment is just right, a single galaxy behind a black hole can appear as a perfect glowing ring around it. We call that an Einstein ring, not because Einstein made it, but because his equations predicted it, and the universe said, yes, that's exactly what happens. Let that settle in, that something so massive can bend light. That light, which always tries to move straight and free, can be forced to curve. And if light can curve, then so can time. You might not be surprised to know that light and time are deeply connected. The speed of light is like a speed limit for the universe. Nothing can go faster, not even time itself. So when light struggles near a black hole, time struggles too. Let's drift a little higher, just far enough to look back at the black hole from a calmer place. From here, it looks small, but endlessly deep. A tiny dark center, surrounded by a blur of light and matter and distortion. It almost looks like an eye, not watching, not thinking, just open, staring into something we can't see from this side. Some believe black holes may be more than simple destinations. They may be connections, portals, pathways. If space can be curved so completely here, might it not connect to another point, another time, another universe? That idea leads us to something called a wormhole. The word doesn't matter much right now. But the idea is lovely. Imagine folding the universe like a piece of paper and poking a hole through. The black hole might be the entrance. The exit? We don't know. Some say white holes might be the other side, places where nothing can go in, only out. We've never found one, but that doesn't mean they don't exist. It only means we haven't seen one yet. And here's another wild thought. What if the universe began with something like a white hole, a place where everything rushed out at once, a great release, a moment of becoming? Some scientists believe that if you could survive the journey through a black hole, if you could pass beyond the singularity, you might emerge into a new universe entirely, a place where time begins again, or flows backward, or spirals. There's no way to know, of course. Not yet, but the questions are beautiful, aren't they? And they remind us of something gentle and important. The unknown is not always frightening. Sometimes it's just quiet, waiting, ready to be understood. Let's float here and feel that thought. The unknown is a space, not a threat. The silence is full, not empty. And time, well, time isn't gone. It's still with us, just stretched, bent, and whispered into different shapes. Right now, as we drift here near the black hole, your own sense of time might be changing. Minutes might feel longer or shorter. That's okay. You're part of the same strange clockwork as the stars now. A slow, steady rhythm that moves not with numbers, but with wonder. Let's keep moving. No destination, no deadline. Just curiosity, just company. There's more to feel, more to see. We'll keep going together. Let's drift a little farther from the black hole now, not because we're done learning from it, but because the view from out here gives us a wider lens. And in that quiet distance, we start to see more of what black holes actually do to time, and how we know any of this is real. You see, black holes aren't just guesses or theories anymore. We've seen them. In 2019, we captured the first real image of a black hole. Not the hole itself. Of course, nothing can escape its gravity, not even light, but the shadow it casts, surrounded by a glowing halo of superheated matter. That halo is called the accretion disk, and it's made up of gas and dust spiraling inward, heating to millions of degrees. That image, taken by the Event Horizon Telescope, showed us the supermassive black hole at the heart of galaxy M87. It's about 55 million light-years away, and it's huge, over 6 billion times the mass of our Sun. Just let that sink in. A single object, invisible at its core, so heavy that 6 billion suns could sit inside it, and it still wouldn't shine. Instead, it bends space around it so tightly that light itself can't climb out. But here's where the time part comes in. According to Einstein's general theory of relativity, the stronger the gravity, the slower time moves. And black holes have the strongest gravity in the universe. So, near the surface of a black hole, the event horizon time slows down drastically compared to a faraway observer. This isn't science fiction. This has been confirmed again and again. We've even measured this time dilation on Earth. There are satellites in orbit right now that run slightly faster than clocks on the ground, not because the electronics are different, but because they're higher up in Earth's gravitational field, where gravity is weaker. It's just a few billionths of a second faster, but it's real. GPS systems have to account for it, or your phone would slowly drift miles off course every day. That's Earth's tiny gravitational difference. Now imagine the same effect, but near a black hole. If you hovered just outside the event horizon, for every hour you experienced, years might pass for someone far away. If you stayed too long, you could return to find entire generations had come and gone. That's not imagination. That's math. That's physics. And we've seen it play out, not with people, but with light. When light climbs out of a strong gravity well, like near a black hole, it gets stretched, its wavelength lengthens, its energy drops. This is called gravitational redshift. It's like the light ages as it escapes. It takes longer to reach us, and when it does, it's dimmer, redder, changed. The photons are still there, but they've been through something, just like time. And even now, we're still discovering more. In 2022, the James Webb Space Telescope began peering into the early universe. And guess what it found? Some galaxies, some of the oldest ever seen, already had supermassive black holes at their centers. That's strange. because we thought black holes took time to grow. You'd need stars to form, collapse, merge, and feed. But these ancient black holes were already giants, only a few 100 million years after the Big Bang. It's like walking into a nursery and finding fully grown adults already reading the newspaper. So now we ask, how did those black holes get so big, so fast? And if black holes were already warping time that early in the universe, could they have shaped the flow of cosmic history? Could they have altered the pace of galaxy formation? We're still figuring that out. But every new image, every burst of light, every distant signal brings us closer. And here's another curious fact. Black holes evaporate. That's right. Over unimaginable stretches of time, they lose mass. Slowly, through a process called Hawking radiation. The idea came from Stephen Hawking in the 1970s. He realized that even in the vacuum of space, quantum effects near the event horizon would allow tiny particles to pop into existence. Some would fall into the hole, others would escape. The result? The black hole loses a tiny amount of mass. It's like a cosmic leak. But it's so slow, so small, that it only matters for the tiniest black holes. The ones with the mass of a mountain might evaporate in billions of years. The big ones, like the one we just visited, they'll be here long after the last stars die, still slowly fading, still distorting time until the very end. And one day, when all the light is gone, when the universe is cold and dark, only black holes will remain. For a while, but even they, in time, will disappear. A universe without stars, without galaxies, just black holes, slowly dissolving into radiation. That's one version of the future. But there are others. Some scientists believe black holes could leave behind something strange. Not nothing, but something smaller, denser, more fundamental. A remnant, a speck of pure space-time. A kind of fossil of collapsed time. We don't know yet. The truth is still hidden in the math, in the particles, in the strange rules of quantum mechanics. But we're getting closer. And as we learn more, the question becomes clearer. Not just, do black holes destroy time? But, what is time? Is it a thing? A dimension? A flow? Or just a way for our minds to make sense of change? Black holes don't answer that question, but they make it impossible to ignore. And they force us to face another truth. We are creatures of time. We age. We remember. Let's ease our way closer to another black hole now. This one is much smaller than the last, but no less mysterious. It doesn't sit in the center of a galaxy like Matey 7's monster. Instead, it's tucked into a stellar graveyard right here in our Milky Way. It formed not long ago, at least, in cosmic terms, when a star many times the mass of our sun ran out of fuel and collapsed inward. That star's core gave into gravity, folding in on itself. The outer layers blew off in a supernova, a flash of light so bright it outshone entire galaxies for a few days. What was left behind wasn't a glowing ember, but a shadow, a place where mass became density, where space curled too tightly to see into, and time, well, time took a different path entirely. Now, the black hole rests in darkness, no larger than a city, but heavier than 3 suns. And here's the wild part. We didn't see the black hole itself. We saw the things it did. It tugged at a companion star nearby. As that star spiraled in, its gas stretched and twisted into an accretion disk, lighting up in X-rays. Telescopes caught the glow, watched the spin, tracked the wobble, and from all that, astronomers said, there's something invisible here, something massive, and it fits the bill. We've found dozens of black holes this way. Most are stellar mass black holes. They weigh a few times as much as our sun, but even these small ones mess with time. If you were to fall toward this black hole, feet first, you'd be in trouble. Gravity near the event horizon isn't gentle. It pulls on your feet harder than your head. This effect has a name, spaghettification. And yes, it's just as unpleasant as it sounds. But more fascinating than the stretching is what happens to time. From your point of view, as you fall in, time feels normal. You breathe, you blink, your thoughts drift just like always. But from my perspective, watching from a distance, your fall slows down. You hover, you freeze, seemingly forever, at the edge of the event horizon. Your last image stretches out into eternity. This is real. It's not science fiction. It's the warping of space-time under extreme conditions. We've even seen stars whip around black holes at speeds of thousands of kilometers per second, especially near Sagittarius A, the black hole at the heart of our own galaxy. These stars help us map the mass of the black hole. We watch them complete orbits and confirm predictions Einstein made over 100 years ago. No other object explains what we see better than a black hole. And so we ask again, are black holes destroying time? Or are they simply revealing how fragile and flexible it really is? Let's visit that galactic core for a moment. Sagittarius A. It's quiet now, not like the ones feasting on nearby stars or swallowing gas in a glowing frenzy. Our black hole is resting, dormant, calm. But it's still there, 4 million times the mass of our sun, and every star within light years of it feels its pull. The way we confirmed Sagittarius A was through a patient 27-year-long observation of a single star named Stu. Astronomers watched it complete a full orbit, swinging close to the black hole and then far away, like a cosmic slingshot. And during its closest pass, the light from Stu changed. It redshifted. Time around it slowed just a little enough that we saw it. That star helped us prove the effects of relativity not in a lab, not with satellites, but on the grandest scale imaginable. It told us, in glowing whispers, yes, time bends. And maybe, just maybe, time can be lost. Now imagine this. Inside the event horizon, time doesn't just slow, it becomes one with space. Direction doesn't mean what it used to. Moving forward might now mean moving inward. You can't turn around. You can't stop. You can't hover at the edge. Once you're past that boundary, the equations tell us your future is fixed, and it leads to the singularity. That singularity is the ultimate mystery. Is it a point? Is it a knot in space-time? Is it even real? Here's the strange truth. Einstein's equations break down at the singularity. They give us infinity's mass concentrated to zero size, density without limit. But infinities, as physicists like to say, are often a sign that we don't fully understand the problem yet. They hint that our math is incomplete, that something deeper is waiting to be discovered. Many scientists believe we need a theory of quantum gravity, a unification of general relativity, which describes the large, and quantum mechanics, which explains the small. Black holes sit at the crossroads of both. They are large and heavy, but the singularity is tiny. They bend space and time, but they also must obey the rules of quantum fields. And here's another twist. Black holes might not be the ultimate information destroyers we once thought. For decades, physicists argued about the black hole information paradox. If you throw something into a black hole, a star, a spaceship, a notebook filled with your deepest thoughts, does the information in those things disappear forever? That would break the rules of quantum mechanics, which say information must be preserved. But in 2022, new research began to shift the view. Some believe that the information isn't lost, just scrambled, hidden in the subtle quantum ripples of the Hawking radiation, escaping over trillions of years. Like burning a book, you can't read it anymore, but the ash and smoke still contain all the atoms. This suggests black holes might not destroy information. And if they don't destroy information, could it be that they don't really destroy time either? Maybe they transform it, reshape it, fold it so tightly that it vanishes from our view, but not from the universe itself. You might notice, just ahead, the soft shimmer of something strange. Not a star, not a planet. It's a kind of glow, but not like the gentle warmth of sunlight or the sparkle of reflected starlight. This glow, it pulses. It dances gently at the edge of a quiet, invisible shadow. We've found another black hole, but this one is feeding. Not in a violent frenzy, not exploding or devouring in an instant, just feeding. A steady swirl of gas and dust circles around it, spiraling inward, heated by friction to millions of degrees. That heat radiates outward, whispering its presence in X-rays we can detect from Earth. And yet, at the center of it all, the black hole itself remains unseen. Reach out, slowly, and feel the warmth on your fingers. It's faint, distant, but real. That heat tells a story of matter falling inward and time unraveling. Let's hover just above the event horizon again. just close enough to sense the pull, but far enough that we don't fall. Look closely, and you'll notice something strange about the gas and light nearby. They're moving, but not like anything we know. They twist in a spiral that tightens the closer they get, until finally, they cross a point where no path leads back. From our view, they seem to slow, and then freeze, forever suspended, just outside the edge. And yet from their own point of view they fall, unstopped. They fall through time the way we move through space. Now listen, can you hear that faint hum? It's not a sound in the usual sense. It's gravitational waves, tiny ripples in the fabric of space-time itself. When two black holes spiral into one another and merge, they send out a shiver not through air, but through space itself. We felt them. In 2015, the LIGO observatories captured the first ever direct evidence of these waves. Two black holes collided over 1 billion light-years away, and the echo reached Earth. The signal lasted just a fraction of a second, but it confirmed something profound. Space is not still. It can tremble. It can breathe. It can remember the motion of things long after they're gone. And time is not separate. It's part of that same fabric. When black holes collide, they don't just bend space. They twist time into a knot, a wave that spreads outward and whispers of ancient cataclysms. Now take a moment. Close your eyes if you like. Imagine that moment, two black holes circling one another faster and faster, closer and closer, until they touch, and then silence. A new black hole forms, more massive than either alone, and with it, a new horizon, a new edge to space and time. We're witnessing time fold over on itself. Not in a fantasy, not in a dream, but in the real, breathing structure of the universe. This is how we know black holes aren't just places where things disappear. They are active players in the shape of time itself. Let's float now toward the center of the whirlpool galaxy. You can see it spinning gently in the distance, arms of stars like swirls of cream in a cup of coffee. At its center, like so many galaxies, waits a supermassive black hole. This one is millions of times the mass of our Sun, and even though it's hidden, we know it's there not because we see it, but because we see what it does. It guides stars in perfect orbits. It bends the light of distant galaxies behind it, making rings and arcs we call gravitational lenses. And, in some galaxies, it flares to life as a quasar brighter than 1 trillion suns, blasting jets of energy across millions of light-years. Imagine standing near that core, watching the stars whip around in dizzying arcs. Feel the spin of the galaxy beneath us. Hear the low hum of radiation drifting from the swirling disk. Time moves differently here. Gravity pulls hard, and clocks tick slow. This is real. We've measured it. Astronauts on the International Space Station experience time a little slower than we do on Earth's surface, just a few milliseconds. But near a black hole, that difference stretches and stretches until it becomes impossible to ignore. It means someone hovering near a black hole could, in theory, watch the universe race ahead. Galaxies collide. Stars are born and die. Civilizations rise and fall, all in what feels like minutes to them. That's how deep the connection is between gravity and time. So again, we ask, are black holes destroying time? Or are they revealing something hidden about its nature? Let's follow that thread deeper. You might remember the name Stephen Hawking. He once asked a daring question: do black holes really trap everything, or can they shrink and evaporate? And it turns out, yes, they can evaporate. Very, very slowly, through a process called Hawking radiation. Don't worry about the complex math behind it. Feel it instead. Picture tiny particles flickering into existence near the event horizon. A pair. One falls in, the other escapes. That escape steals just a little energy from the black hole. And over billions or trillions of years, those tiny escapes add up. Eventually, even the largest black holes will fade. Not in an explosion, not in a bang, just a slow, quiet fade into darkness. And if that's true, what happens to the time that fell in? Where does it go? Some physicists think the black hole keeps a kind of memory, a quantum imprint of everything it absorbed, not visible, not readable, but there, hidden in the ripples, folded into the curve of space. It means time isn't lost. It's encrypted, whispered, preserved in a way we're only just beginning to understand. So as we drift farther now, past the edges of these galactic cores, I want you to keep your senses open. Not just your eyes and ears, but that deeper sense of wonder, the part of you that knows time isn't just the ticking of a clock. It's a river, a song, a thread woven into every star. And out here, near these black holes, that thread gets tangled, not destroyed, transformed. And we are the lucky ones, the quiet travelers who get to witness it, piece by piece, moment by moment, as the universe reveals its hidden side. Feel the gentle pull now as we edge closer to one of the strangest ideas in physics. The idea that black holes might connect distant places in space and time. Imagine, just for a moment, that a black hole isn't simply a trap, but also a bridge, a tunnel through the universe. Physicists call these hypothetical tunnels wormholes. Picture space like a sheet of paper. If you fold it, two distant points touch. A wormhole would be that fold, a shortcut through the fabric of reality. Could black holes be gateways to other parts of the cosmos? Or even other times? No one has found a wormhole yet, but the math allows for it. It's a tantalizing possibility, one that challenges how we think about space, time, and the flow between them. Now drift inward again, toward the edge of a black hole's event horizon. This invisible line is where gravity becomes so strong that escape is impossible. It marks the point of no return, the boundary between the universe we know and the unknown. Imagine standing just outside this line, feeling the tug on your body, the stretching of space itself. From your perspective, time slows down. 1 minute out here might be hours closer in. Watch carefully, and you see photons, packets of light, hover near the horizon, looping in tight orbits before spiraling inward. This dance of light and gravity is how we measure the size of a black hole, and it tells us more about time, how it bends and stretches under such extreme forces. Scientists have even captured the shadow of a black hole, a silhouette against the glowing gas around it. The Event Horizon Telescope, a global network of radio dishes, worked like a single giant eye, peering into the heart of the galaxy Métis 7 to catch the first ever picture of a black hole's shadow. That image wasn't just beautiful, it was a glimpse into the warping of space and time. The black hole's shadow is bigger than the event horizon itself, a trick of light curved by gravity. It's a place where time stands on the edge, caught between being and nothingness. Reach out your hand and feel the echo of that moment, the pulse of photons captured from billions of light years away, bringing us news from the very edge of time. Let's shift focus for a moment and think about time itself, not as a straight line, but as a fabric woven into every corner of the universe. Einstein's theory of relativity taught us that time isn't absolute. It flows differently depending on speed and gravity. If you zoom through space at nearly the speed of light, time slows for you compared to someone standing still. This effect, called time dilation, has been measured with atomic clocks on airplanes and satellites. Near black holes, this dilation becomes extreme. Close to the event horizon, 1 second for you might be years for someone far away. Imagine someone watching you fall in, decades passing outside, while you cross the horizon in moments. The universe ages without you, but you experience time normally. It's a strange divide, a paradox of perspective. Now, let's think about the ultimate fate of matter swallowed by a black hole. When something crosses the event horizon, it's lost to our view. But where does it really go? Inside, space and time swap roles. Moving inward toward the singularity is like moving forward in time. You can't turn back. The singularity itself, where density becomes infinite and our laws of physics break down, remains a mystery. Some theories suggest that instead of a single point, the core might be a fuzzy quantum region, where particles and waves dance in a chaotic but orderly way. Others propose that the singularity could be a gateway, connecting to a new universe born inside the black hole, a cosmic seed sprouting from the death of a star. If that's true, then black holes might be more than endings. They could be beginnings. This idea connects with the multiverse theory, the notion that our universe is just one bubble in a vast cosmic foam of many universes. It's a wild thought, but one that helps us see time not as destroyed, but as transformed, branching, and endlessly evolving. As we drift now past distant galaxies and glowing nebulae, imagine time stretching like a rubber band. It can snap, stretch, loop, and twist in ways we're only beginning to understand. Black holes teach us that time isn't fixed. It's fluid, it's malleable, and it's tied inseparably to space. Each new discovery pulls us deeper into that mystery. We watch stars orbit, light bend, and gravity ripple. We listen for whispers of collisions, echoes of beginnings and ends. Picture yourself drifting closer to a black hole again, this time one a few times the mass of our Sun. These are called stellar mass black holes, born from the collapse of massive stars after they run out of fuel. When a star much larger than our Sun exhausts its nuclear energy, gravity wins the battle, squeezing its core tighter and tighter until it collapses into an infinitely dense pointer singularity, wrapped inside a boundary called the event horizon. Inside this boundary, physics as we know it twists and folds. Gravity's grip is so fierce that even light can't escape. That's why we call it black. But what does that mean for time? We learned from Einstein's theory of general relativity that gravity affects time. The stronger the gravity, the slower time passes relative to a distant observer. This is called gravitational time dilation. Near a black hole, this effect becomes extreme. Imagine you have a clock with you, and you're floating safely at a distance from the black hole. Your friend decides to hover just above the event horizon with their clock. To you, their clock ticks more and more slowly as they approach the horizon, eventually seeming to nearly stop. But your friend experiences time normally. This difference isn't just a trick of perception, it's a real, physical effect. This means that if you watched someone fall toward a black hole, you'd see their movements slow down, stretched out across eternity as they hover near the edge. Yet, from their point of view, they cross the horizon without noticing any sudden change in the flow of time. This phenomenon raises the question, does time end at a black hole, or does it just stretch so much that it feels like it stops? Now, let's bring in something else. Hawking radiation, named after the brilliant physicist Stephen Hawking, who showed that black holes aren't entirely black after all. Thanks to quantum effects near the event horizon, black holes slowly emit particles and energy. This process means that black holes can lose mass over incredibly long timescales, eventually evaporating completely. This is crucial, because if black holes evaporate, then they don't hold on to everything forever. But what happens to the information about everything that fell in? Physicists call this the information paradox. According to quantum mechanics, information can't be destroyed, yet black holes seem to erase it. Modern theories suggest that the information might be encoded on the event horizon itself, stored holographically. The event horizon acts like a cosmic ledger, keeping a record of everything that crosses it, even as the black hole slowly shrinks. This idea, the holographic principle, hints that our universe itself might be a kind of hologram, with the information about the entire volume of space encoded on a boundary. So time and information aren't destroyed inside black holes, they're transformed and preserved in a new way. Think about the enormous black hole at the center of our Milky Way galaxy Sagittarius A. It's about 4 million times the mass of our Sun. Over decades, astronomers have tracked stars orbiting this invisible center with incredible precision. Their paths reveal the mass and influence of the black hole, proving its existence indirectly. By measuring these orbits, we can test general relativity in the strong gravity regime near the event horizon. So far, the predictions hold true. Space and time behave exactly as Einstein described, bending and slowing in the presence of this massive object. Now, imagine the flow of time near Sagittarius A compared to Earth. The difference is tiny for us, but for an astronaut near the black hole's event horizon, time could stretch so much that a few hours there equal thousands of years here. This is not just theory, it's based on precise measurements and calculations. But what about the singularity itself, that point of infinite density where our current physics breaks down? Here lies the edge of our understanding. At the singularity, gravity crushes matter into a state where space and time cease to be distinct. Quantum gravity, a field still in development, aims to reconcile Einstein's gravity with quantum mechanics to describe what really happens inside. Some ideas suggest the singularity might not be a point, but a region of quantum fuzziness. Others propose that singularities don't actually form. Instead, some unknown quantum process prevents the formation of infinite density. Until we unlock that mystery, the question of whether black holes destroy time remains open. But the evidence leans toward black holes bending, stretching, and transforming time, not erasing it completely. There's also fascinating research about what happens if you fall into a rotating black hole, called a Kerr black hole. Unlike the simple non-rotating black hole, the rotating kind drags space and time around with it. This frame-dragging effect can create a ring-shaped singularity, theoretically allowing paths through the black hole that avoid the singularity altogether. If true, this could mean that time behaves very differently inside these spinning giants, perhaps even looping or connecting different parts of the universe. Finally, consider how black holes affect the universe on large scales. Their gravitational pull helps shape the structure of galaxies. They regulate star formation by controlling gas flows and even power some of the brightest objects we observe, quasars. In all these ways, black holes are engines that influence time and space on the grandest scales. So as we float here, surrounded by stars and stretched by gravity, remember, black holes are not time's end. They are its most extreme expression. They teach us how time bends, how information weaves, and how the universe holds on to its stories. The journey through their mysteries continues, and you are right here, witnessing every twist and turn. Imagine now that we're floating just outside the event horizon, watching a glowing disk of gas and dust swirl around the black hole. This is called the accretion disk, where matter spirals inward, heating up to millions of degrees, shining brightly in X-rays and other energetic light. It's a spectacular light show powered by gravity's grip on time and space. Because the black hole's gravity is so intense, the material in this disk moves at incredible speeds close to the speed of light near the inner edge. This means time slows down for the gas there, relative to us far away. Each particle of gas experiences time differently, depending on how close it is to the black hole. This creates a strange and beautiful effect called gravitational redshift. Light emitted near the black hole loses energy climbing out of its gravity well, shifting toward the red end of the spectrum. So when we observe this light, we're seeing the story of time stretched and slowed by gravity. This interplay between light, time, and gravity lets astronomers test Einstein's ideas in the wildest conditions. Observations of accretion disks around black holes confirm predictions about how gravity warps time and bends light. Now let's step back and consider time on a universal scale. Our universe has a cosmic clock, the cosmic microwave background radiation. This faint glow left over from the Big Bang acts as a time capsule, telling us how long ago everything began about 13.8 billion years. Black holes formed shortly after the first stars lit up, their gravity-carved structure from chaos, anchoring galaxies and shaping cosmic evolution. So they have been part of time's unfolding since near the very beginning. This leads to a fascinating thought. Black holes might connect the earliest moments of time to its distant future. Because they hold mass, energy, and information for such long spans, black holes act like slow clocks themselves. Even though time flows differently near a black hole, for distant observers, the black hole's lifespan is unimaginably long, many billions or even trillions of years for the biggest ones. So, in a way, black holes stretch time across the universe's history. Imagine you could live near a supermassive black hole for just a few hours, then return home. You'd find the universe aged billions of years in your absence. Time dilation near black holes turns into a kind of time travel forward, not backward. Now, think about the black hole's role in the ultimate fate of the universe. Some scientists speculate that as the universe ages and expands, black holes will be among the last remaining objects before they too evaporate via Hawking radiation. In this slow cosmic dance, black holes remind us that time isn't just a background flow, but an active player in the universe's evolution. And here's another intriguing fact. Gravitational waves, ripples in space-time caused by violent cosmic events, can come from black hole mergers. When two black holes collide, they send waves traveling through the fabric of space and time. In 2015, the LIGO Observatory detected these waves for the first time, confirming a key prediction of general relativity. These waves carry information about time's fabric vibrating under extreme gravity. Listening to these cosmic vibrations is like hearing the universe's heartbeat, time itself ringing with the echoes of black hole collisions. These detections open a new window to explore how time behaves under the most intense conditions imaginable. Let's take a moment to imagine time as a river flowing around rocks. Black holes are massive boulders in this river, creating eddies and whirlpools that twist and shape the flow. Time flows differently near these stones, slower and warped. The more massive the black hole, the larger the distortion. Supermassive black holes create wide, slow zones in time, while smaller ones cause sharp, intense warps. This analogy helps us feel time's elasticity and how black holes serve as natural laboratories for its extremes. Next, consider the concept of entropy, a measure of disorder or information content in a system. Black holes have entropy too, proportional to the area of their event horizon. This surprising fact links thermodynamics, gravity, and quantum theory. It suggests that black holes store information not in their volume but on their surface, the event horizon, which relates back to the holographic principle. So time, information, entropy, and gravity all weave together in black holes, offering clues to a unified theory of physics. Now, as we continue this journey, look up at the sky and imagine countless black holes hidden in the darkness. Many lie dormant, quietly pulling in gas and stars, while others blaze as active centers of galaxies. Each one is a monument to time's complex nature, where moments stretch, information transforms, and mysteries deepen. We've traveled far in this exploration, yet the questions keep flowing. Do black holes destroy time? The evidence says no, they bend and stretch it, hiding its secrets but never erasing them. Time near a black hole is a river that slows, a clock that runs differently, a story written in the language of gravity and light. And through this voyage, you've been more than an observer, you're a fellow traveler in time's great adventure, feeling the pulse of the cosmos and the wonder of the unknown. Now, as we float a little farther from that glowing accretion disk, let's consider what happens to time inside a black hole, the place beyond the event horizon, where no light or matter escapes. This boundary is like an invisible curtain, hiding the secrets beyond. You might imagine that inside this dark veil, time itself could come to an end. But what does that really mean? Inside, space and time swap roles in a sense. The direction we call time outside becomes like a direction in space inside, pulling everything inevitably toward a point called the singularity. This singularity is thought to be infinitely dense, where all the black hole's mass is crushed into an unimaginably small space. It's a place where our current understanding of physics breaks down, where the familiar rules of time and space no longer apply. Because of this, some physicists say the singularity is a sign that our theories need to evolve. Time as we know it may lose its meaning here, but what replaces it is still a great mystery. Picture the singularity as the ultimate end point of time for anything that falls inside. Once crossed the event horizon, all paths lead forward toward the singularity. There's no turning back, no pause, no escape. Yet, paradoxically, from an outside observer's point of view, something falling in appears to slow down, frozen near the event horizon, as if time nearly stops there. This strange contradiction highlights just how weird time becomes near black holes. Now, here's a mind-bending fact. Stephen Hawking showed that black holes aren't completely black. They emit faint radiation now, called Hawking radiation, due to quantum effects near the event horizon. This radiation means black holes can slowly lose mass and energy over extremely long timescales. This discovery links quantum mechanics, gravity, and thermodynamics in a beautiful, mysterious way. It suggests that black holes have a temperature and can evaporate, returning energy back to the universe. Think about what this means for time. The black hole's lifetime can be enormous, far longer than the age of the universe for the biggest ones, but it's not infinite. Eventually, it fades away, hinting that time continues beyond the black hole's existence. Let's also consider the famous information paradox. According to quantum physics, information can never be destroyed. But what happens to the information about the matter that falls into a black hole? If black holes destroyed information, it would break fundamental laws of physics. But Hawking radiation seemed to suggest information was lost when black holes evaporated. This puzzle has driven decades of research and heated debate. Recent theories propose that information might be preserved, somehow encoded on the event horizon, or released slowly through radiation. This connects deeply with how time and information interact near black holes. Imagine that the surface of the black hole is like a cosmic memory bank, storing all the details of what has fallen in. Time, in this view, doesn't get destroyed, it's recorded, transformed, and preserved in subtle ways. Another incredible idea involves black hole complementarity, which suggests that the experience of time and space depends on the observer's position. For someone falling in, time flows normally until the singularity, but for an outside observer, infalling objects freeze in time at the horizon. This dual perspective challenges our concept of a single, absolute timeline and introduces the possibility that time is relative in profound ways. Let's also talk about the spinning black holes, known as Kerr black holes. These rotate at incredible speeds, dragging space and time around them in a process called frame dragging. Imagine being caught in a whirlpool, where not just water but time itself is twisted and pulled along. Near a spinning black hole, this frame dragging can create regions where time loops or paths curve back on themselves. This leads to theoretical possibilities of closed, time-like curves paths through space-time that loop back in time, suggesting the potential for time travel within certain exotic regions. While these ideas remain speculative and face huge challenges, they show how black holes push the limits of what we think time can be. As we drift in this cosmic sea, notice how these phenomena stretch the concept of time from something fixed and steady to something flexible, dynamic, and deeply mysterious. We're learning that time near black holes isn't simply destroyed or halted, it's reshaped, entangled with space, energy, and information in ways we're still uncovering. And remember, each black hole we observe, from stellar remnants to supermassive giants at galactic centers, is a unique laboratory where these strange time effects play out on different scales. This richness gives astronomers powerful tools to test physics, observe gravitational waves from black hole mergers, and refine our picture of how time behaves under the universe's most extreme conditions. It's a breathtaking idea that every black hole might be the birthplace of a new universe, a cosmic seed sprouting its own time and space, completely separate from ours. Imagine, if you will, that the singularity inside a black hole is less a dead end and more a portal to a fresh beginning, where time as we know it resets or takes on an entirely new meaning. This notion comes from some interpretations of cosmology that blend black hole physics with the idea of baby universes budding off from our own cosmos. If true, time inside these new universes could flow independently, unfolding their own unique stories far beyond our observation. Now, as you ponder this, you might wonder about how time dilation, the stretching and squeezing of time, plays a role here. Remember that close to a black hole, gravity is so intense it slows down time dramatically for anything nearby, relative to an outside observer. So, if you were somehow watching from a safe distance, you'd see processes near the black hole crawl almost to a halt. But for someone falling in, time would feel normal, ticking steadily, until that inevitable encounter with the singularity. Scientists speculate that this difference might mean that inside black holes, the flow of time becomes disconnected from our familiar experience, maybe even becoming layered or multidimensional. And speaking of layers, quantum gravity theories like loop quantum gravity or string theory offer speculative pictures where time isn't fundamental but emerges from more basic building blocks. In such models, black holes could be places where time unfolds differently, fractured into discrete moments, or woven into complex quantum threads. Imagine time as a tapestry. Near black holes, the weave might twist and knot, creating patterns that seem strange or paradoxical compared to the smooth fabric we know. Some physicists even propose that what we perceive as time inside black holes might freeze in a certain sense and no ending, but paused or locked until some cosmic event releases or transforms it. Others have speculated about timeless states inside black holes, where the usual notion of before and after collapses entirely, replaced by a kind of eternal now. If you reach out to touch this concept, it feels like the ultimate mystery, the idea that time, that constant companion of our daily lives, could lose all meaning, become fluid, or fold back on itself. And what about the edge of the event horizon itself? Some theories suggest it might be a kind of membrane that encodes the history and flow of time for everything that has passed through it. In this view, time isn't destroyed but transformed, recorded in patterns of energy and information that ripple on the boundary, even as the black hole changes and ages. This ties into the black hole's entropy, a measure of disorder or information content, which is proportional to the area of the event horizon, not its volume. This surprising fact hints that time and information near black holes are deeply connected in ways we're only beginning to grasp. As we drift through these ideas, it's clear that the simple question, "Do black holes destroy time?" opens a vast and complex landscape of possibilities. Some say yes, that time ends abruptly at the singularity. Others suggest time is preserved, transformed, or even multiplied inside these cosmic monsters. And still others believe that black holes challenge our very understanding of time, urging us to rethink what time is and how it behaves at the universe's extremes. Imagine drifting closer once again to the heart of the black hole's mystery, feeling that pull, that strange silence where space and time twist like the threads of an ancient tapestry. The deeper we go, the more we uncover about how time might behave in these extreme places. One fascinating idea that scientists discuss is called time dilation. On a colossal scale, picture a clock near the event horizon, ticking slower and slower as it approaches the edge of the black hole. From a distance, you'd see that clock almost freeze, time stretching endlessly. But for someone holding the clock, time flows normally. This isn't science fiction, it's a real consequence of gravity's effect on time, confirmed by experiments near Earth's own gravity wells. This leads to a mind-bending question. If time near a black hole slows down so drastically, could it mean that time never truly ends there? From an outside observer's view, anything falling in appears frozen in time, forever lingering on the edge. So, in a sense, time is preserved at least visually, even if from the traveler's perspective, their experience is brief and intense. Now let's stretch this idea further. Some physicists speculate that the black hole's event horizon acts like a cosmic scrambler, or membrane, storing information about everything that falls in. This concept relates to the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary surface, kind of like how a hologram stores a three-dimensional image on a two-dimensional surface. If time and information are linked this way, then even if matter and light vanish past the event horizon, the history of what fell in is somehow preserved, woven into the fabric of space-time around the black hole. This preservation hints that time might not be destroyed, but transformed into a different form of existence, one written in the language of quantum information. And here's where the story takes an even stranger turn. Black holes aren't just static objects. They can spin, creating what's known as a Kerr black hole. The spin drags space-time around with it, twisting the very dimensions of time. Imagine standing near one of these spinning giants. Time itself would swirl, creating regions where the past and future become tangled. In these regions, the paths through time might loop back on themselves, creating what scientists call closed time, like curves. These are theoretical pathways where time travel could, in principle, happen. It's like a cosmic Mobius strip for time, looping endlessly, where cause and effect get blurred. Of course, no one knows for sure if these loops exist in reality, or if the universe protects itself from such paradoxes. Theories suggest that if time travel were possible, some chronology protection might prevent paradoxes, preserving the logical order of events. Let's also consider the fate of the information swallowed by black holes. This puzzle, known as the black hole information paradox, has puzzled scientists for decades. Quantum theory says information can never be destroyed, but classical black holes seem to erase everything inside. Recent breakthroughs hint that the information isn't lost, but encoded in subtle quantum correlations, possibly radiated back into space through Hawking radiation, a faint glow emitted by black holes as they slowly lose mass over unimaginable timescales. If Hawking radiation carries away information bit by bit, then time and information continue their journey, not destroyed but dispersed. This slow leak of information suggests that black holes could be temporary way stations in the cosmos rather than eternal prisons. Speaking of timescales, consider that some black holes take longer than the current age of the universe to evaporate completely. Imagine a black hole quietly fading over many billions or trillions of years, its grip on time and space gently loosening. This cosmic patience invites us to think differently about time near black holes. They might stretch moments into eons and slowly release the past back into the universe in whispers of radiation. Now, picture the cosmic dance when two black holes collide, a violent, titanic event sending ripples through the fabric of space-time called gravitational waves. These waves carry information about how space and time stretch, compress, and ripple, like a vast pond disturbed by a cosmic stone. Listening to these waves with instruments like LIGO and Virgo has opened a new window into the universe's most extreme environments, revealing how time itself bends and flexes in black hole mergers. As we feel the echo of these collisions, we realize that time near black holes isn't static or destroyed. It's dynamic, alive, and deeply entwined with space, energy, and information. So, as we continue our journey through this cosmic enigma, remember that black holes challenge everything we think we know about time. They don't simply erase it, but transform, stretch, and sometimes twist time into forms that push the limits of imagination and physics. Feel the awe in this cosmic riddle-the-universe's way of reminding us how much there is still to discover and how time, that familiar friend, can become stranger than we ever dreamed. There's so much more ahead about the quantum foam near singularities, how gravity and quantum mechanics might unite, and how black holes might hold clues to the ultimate nature of time itself. Picture yourself floating peacefully in space, far from any star or planet, when you begin drifting slowly toward a black hole. At first, it feels like any other gravitational pull, a gentle tug, a quiet invitation to come closer. As you approach, the pull grows stronger, but strangely, you might not notice much at first. Space around you feels calm and vast. Now, imagine looking back at the distant stars. They shine steadily, but as you near the black hole's event horizon, invisible boundary beyond which nothing can escape, they seem to stretch and shimmer, their light bending and twisting in strange ways. This bending of light is called gravitational lensing, and it's like seeing the universe ripple and distort around you. If you were watching from afar, you'd see something even more surreal. As you fall closer, time for you would slow down from their perspective. To an outside observer, you would appear to move slower and slower, as if frozen in time, hovering just above the event horizon. It's like watching a slow-motion dance that never quite ends. But for you, the experience feels completely different. Time flows normally, steady, and sure, but other sensations would quickly become intense and strange. The gravity near the black hole is not uniform. If you fell feet first, the pull on your feet would be much stronger than on your head. This difference stretches you out in a process often called spaghettification. Imagine your body elongating like a piece of cosmic spaghetti, stretched thinner and thinner as you get closer to the center. At the same time, you'd feel a squeezing from the sides, as gravity compresses you horizontally. The forces are enormous, far beyond anything we experience on Earth. Yet, in those moments, your mind might be too overwhelmed by the surreal environment to fully grasp the physical sensations. Visually, the view outside would be astonishing. The stars and galaxies behind you would warp into swirling rings of light, circling the black hole's dark center. You might feel as though you're inside a cosmic whirlpool, pulled deeper into a realm where space and time blend together. Once you cross the event horizon, things change in ways that challenge our usual understanding. According to Einstein's theory, nothing, not even light, can escape beyond this point. To the outside world, you've vanished. But for you, falling inward, the journey continues. The interior of the black hole is a realm where space and time swap roles. In a sense, moving inward feels like moving forward in time, relentlessly toward the singularity, the mysterious core where density and gravity become infinite. This relentless pull toward the singularity means that, from your perspective, there is no turning back. It's like sliding down an endless slope, time pressing forward as space narrows. Scientists imagine that as you approach the singularity, the known laws of physics break down, and space-time itself becomes so curved and warped that concepts like before and after lose their meaning. No one can say for sure what this would truly feel like. Some theories suggest that the singularity might not be a point, but a fuzzy region governed by quantum effects, a realm where our classical ideas of time and space dissolve. If you close your eyes in this imagined fall, you might sense a mixture of awe and profound mysteria, feeling of moving beyond everything familiar towards something utterly unknown. For those watching from a distance, your journey freezes near the horizon, but inside, you're swept onward through the cosmic currents of warped time. This duality, the frozen outside view and the inward, unstoppable flow, reflects the deep paradox at the heart of black holes and time itself. So, if you reach out, imagine feeling both the immense pull of gravity stretching you and the eerie calm as time itself slows and twists around you. It's a journey that invites us to think about how fragile and flexible time really is in the universe's most extreme places. Picture the very moment you cross the event horizon. It's not like stepping through a door or passing into a new room. Instead, it's like entering a place where the rules you've known your whole life begin to twist and fold. The sky behind you, the vast cosmos you once knew, fades away. There's no going back. Time itself seems to change its rhythm, like a song slowed down to the point where every note lingers and stretches. Inside this mysterious boundary, time no longer flows in the steady, familiar way it does back home. Here, the roles of space and time swap places in a strange cosmic dance. Instead of moving freely through space while time ticks forward steadily, inside the black hole, moving forward in time feels like moving closer and closer to the center of the singularity. You can't stop or turn around, because time forces you onward. Imagine it like being on a runaway train that can only speed toward the unknown. You're carried along by the unstoppable current of time itself, unable to pause or reverse. Each moment brings you closer to the singularity, the heart of the black hole, where everything we understand about physics breaks down. Now, as this happens, strange things might occur to your sense of reality. Scientists suggest that near the singularity, the fabric of space-time becomes so warped that past, present, and future could all blur together. Imagine memories, moments, and possibilities folding into one another like a cosmic kaleidoscope, where time's usual order dissolves. There's a poetic mystery here. Black holes might be places where time doesn't just end or slow, but where it folds back on itself or transforms into something else entirely. Some theories suggest that at the singularity, time might lose its meaning, becoming a sort of timeless void, or a place where all moments exist simultaneously. This idea invites us to rethink what time really is. Is it a steady river flowing in one direction, or is it a more fluid, malleable dimension that can twist, pause, or even rewind under extreme conditions? Outside the black hole, the universe continues on, ticking away with its familiar rhythm. But inside, time's flow becomes mysterious and uncertain, as if caught in a cosmic riddle. Here's another mind-bender. What if black holes are gateways to other places or times? Some speculative ideas propose that the singularity might connect to a white hole, a theoretical opposite where everything spewed in a black hole could emerge somewhere else, maybe even in another universe. While this remains science fiction for now, it paints a picture of black holes not as destroyers of time, but as bridges or transformations of it. Time inside could curve back, loop around, or even sprout into new dimensions, far beyond our current understanding. Feel the vastness of this mystery pressing around you, like standing on the edge of an endless ocean of possibility, where every wave is a ripple in time itself. And as you float here, wrapped in the quiet hum of warped space-time, you begin to sense how much our universe still holds secrets about the nature of time, secrets hidden deep within these cosmic giants. So, here we are, drifting at the edge of everything we can imagine about black holes and time. It's like standing on the shore of an infinite ocean, watching waves roll in and disappear beyond the horizon, knowing that no matter how far you reach, the water keeps going, deeper and more mysterious than any eye can see. Feel the gentle pull of gravity beneath your feet, even if you're floating weightless. It's the universe's invisible hand, guiding us toward the heart of a question that's as old as curiosity itself. What really happens when time meets a black hole? You might imagine it's terrifying or overwhelming, but somehow there's a calmness here too, a strange serenity in facing the unknown. Like gazing into the night sky full of twinkling stars, each one a story, a secret, a spark of life. And time, oh time. We usually think of it as steady, predictable, like the ticking of a clock. But near a black hole, time becomes a shapeshifter, a playful trickster bending and folding itself in ways that twist our understanding. It can stretch into forever, or compress into a moment, all depending on where you stand, or rather, where you fall. You and I, companions in this cosmic journey, are explorers of the impossible. We travel through ideas, theories, and possibilities, knowing that each answer we find opens new doors of wonder. Imagine the paradox that a black hole, often thought of as a destroyer, might actually be a creator, a birthplace for new universes, or a seedbed for time itself. A place where endings are beginnings, and the boundaries between past, present, and future dissolve like mist. And what about you? Here with me now. You're not just a listener, you're a traveler, a witness to the universe's deepest mysteries. Reach out and feel the vastness that stretches all around us. Hear the quiet pulse of the cosmos, the distant hum of galaxies swirling in silent dance. Even if we can't step inside a black hole ourselves, our minds can. We can imagine what it feels like to fall through that threshold, to experience the stretching and twisting of time, to touch the edge of reality and glimpse the infinite beyond. It's humbling and exhilarating all at once, because black holes remind us how much we don't know, how much there still is to discover. They invite us to keep questioning, dreaming, and exploring. So, as we float here together, at the brink of the great cosmic unknown, remember this: time is not just a measure of moments passing. It's a mystery wrapped in light and shadow, woven through space and gravity, a story still being written. And perhaps, just perhaps, the journey itself, the wonder of wondering, the thrill of not knowing is the greatest part of all. Thank you for coming along on this quiet voyage through space and time. If your mind is spinning with questions or your heart is touched by the vastness, you're exactly where you're meant to be. And as always, if you like listening to quiet stories about space and stars, please tap the like button. It helps others find this peaceful place too. And if you want to come back for more calm journeys through the universe, please like and subscribe. Enjoy what I do here, and let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. So, let's keep looking up together, not just for answers, but for the endless beauty of the questions themselves. Because in this vast, swirling cosmos, the story of black holes and time is still unfolding, and the adventure never really ends.